behave very much like a carbon anion adjacent to the pi bond. And we know that the enol is in equilibrium with the keto form. But we know that the equilibrium lies very much toward the carbon-oxygen double bond. And then the equilibrium constant is on the order of 10 to the minus 7 for aldehydes, and on the order of 10 to the minus 9 for ketones, where the enol is a very minor component of the equilibrium mixture. Nevertheless, the enol form, even though it's a very small component of the overall mixture, can be significant in reactions. So this carbon-carbon double bond in the enol form can undergo some addition reactions that you would expect for an ordinary carbon-carbon pi bond. To convert the ketone to the enolate, one can use a strong base like LDA, diisopropylamide, and these reactions, because of the strength of the base, are typically done at low temperature, minus 78 degrees C, being a dry ice bath. And under those conditions, the reaction is irreversible. We have our negatively charged isopropylamide ion moving one of these hydrogens and pushing a pair of electrons out onto the oxygen, which also like to develop, form the lithium enolate. Typically, the lithium diisopropylamide is actually generated in situ by treating diisopropylamine with an alkyl lithium compound like lithium. The lithium is a strong base and deprotates the diisopropylamine to form the diisopropylamide ion. Usually, lithium can be purchased in hexane solution, so we just add diisopropylamine to an ether solvent. This is typically done in ether jet. Inert solvents is not likely to be reacting with strong base, so we generate the diisopropylamide, and then we drip the ketone into the solution of diisopropylamide and gradually convert it to enolate. Once you form this enolate, it can react with alkyl halides, for example, to do an SN2 displacement reaction where the pi bond comes in and displaces iodide to form an alkyl carbonyl compound. The reaction is somewhat problematic, though, because there's still another acidic hydrogen here. In addition to the two acidic hydrogens over here. So it's quite possible for multiple alkylation and if one were to start substituting a neal compound, there are now two possible potential products. And if we use a weaker base, equilibrium mixture will give, as a major product, the more stable, more substitute double bond, and as the minor product, the less substituted double bond. And it will typically give those in about an 80-20 mixture, depending on the structure. Which, after treating with methane, will result in a mixture of 2,2-dimethyl and 2,6-dimethyl cyclohexane. That's not particularly useful synthetically, right? To have multiple alkylation or to have a mixture of different alkylation products where your product of the initial alkylation can then react further to give either a 2,2 or 2,6 product. So if we're going to use this synthetically, we're going to have to use some rather special conditions in order to make sure that we get what we want. We can ask ourselves, what's the equilibrium constant for this reaction? I said it was effectively irreversible. So why is it effectively irreversible? The product, of course, of the decoordination is to come back to disopropyl, and we know that the pKa of ammonia is about 35. It's actually somewhat higher for disopropyl because the electron donating alkyl groups destabilizing the negative charge. That's about 36. But we know that the pKa of the alpha hydrogen, or ketone, is in the 20 to 22 range. This is a much better acid than disopropyl, and if we take 20, then the equilibrium constant would be about 10 to 16. And if we take 22, be about 10 to 14. So we got about a 10 to the 14th to a 10 to the 16th equilibrium constant. That goes to completion, even at minus 78 degrees. In the case of potassium T-butoxide, though, the other product, after it deprotonates that hydrogen, is tertiary butanol. Okay, and that is only 18, which means that the equilibrium constant for this reaction is actually 10 to the minus 2 if we take pKa of 20 here. Which means the equilibrium actually lies towards the ketone, not towards the enolate. And that is what allows equilibrium to occur, because the enolate ion itself is a strong enough base. So if we form this enolate ion, it can react potentially with itself, its starting material here, and forming the other enolate. And that can go either way until we reach our equilibrium rate. So if we allow equilibrium to be reached, then we have no choice in the case of potassium T-butoxide, because the equilibrium constant is 10 to the minus 2, which means it actually is more likely to deprotonate itself than to be deprotonated by the weaker base T-butoxide. We have no choice. We're going to get an 80-20 mixture, which means we're going to get a mixture of products, unless we can think of some way of trapping one of these enolates and isolating it by itself. In the case that we have on the top here, where we have lithium disopropyl mid, which is a very strong base, we can potentially keep it at minus 78 degrees, preventing from forming that mixture of enolates. So there are some complications to enolate alkylation. that enolate alkylation is never synthetically useful. Enolate alkylation can, for example, be quite useful if there is only one alkyl hydrogen, which means only one possible enolate can be formed. And we can use a suitably strong base. Acid hydride is another base that's often used when you're not worried about multiple enolates. Hydride ion is conjugate base of hydrogen gas, which has a pKa about 38, which means that our equilibrium constant for the reaction of potassium hydride for the enolate can be calculated as approximately 10 to the, we assume this pKa, let's assume this pKa is around 22. So our equilibrium constant is again around 10 to the 16th, because hydrogen gas is a little bit less acidic than the dipropylene. So we can get this reaction to go to completion, and if we keep it fairly cold, it's going to stay as this enolate. The alkylation reaction is generally limited to either methyl or primary alkyl halides, because the base is strong enough that if we treat it with a secondary or tertiary alkyl halide, we're just going to get E2 elimination. So if I were then to treat this with methane, I don't have to worry about elimination at all because there's no beta hydrogen. I can add a third methyl group. I can expect to get good yield. So a T-butyl group on one side of that ketone. So this is synthetically useful because there's only one alpha hydrogen, which means only one possible enolate. We don't have to worry about multiple alkylation, and we're using a alkyl substrate that's incapable of E2 elimination. Even if we try a primary substrate here, there's enough steric hindrance at the carbon of the enolate ion that we might have to worry about E2 elimination. So it's a little bit limited. You can also make this synthetically useful for a compound like 2-methylcyclohexanone. By very carefully controlling the order of addition of your reagents. So if instead of adding the lithium disopropylamide to 2-methylcyclohexanone, we add the 2-methylcyclohexanone to the lithium disopropylamide, start with our LDA. Yep. And then slowly add our 2-methylcyclohexanone to the solution of LDA. So we keep a high concentration of LDA and a low concentration of the carbonyl compound. What we hope is that once we form enolate, it's not that likely to run into another carbonyl compound. Because of the steric hindrance of the lithium disopropylamide, will remove the more accessible hydrogen want to make sure that once the enolate reacts with this to form a product, space here. Again, it's an SO2 reaction, so we get our methyl group. We want to make sure that that product isn't likely to run into more enolate. And we don't want this enolate to deprotonate that enolate. What we want to do is we want to keep the concentration of this high and the concentration of the enolate kept low. So that when we put the enolate in, it's going to run into the iodoethane before it runs into the product. So again, we need to add the enolate solution slowly. To a solution of the alkyl halide, rather than adding the alkyl halide to the enolate. So by starting with our strong base, gradually, slowly adding the carbonyl compound to the strong base, and then slowly adding that solution to a solution of alkyl halide, we can actually get a pretty good yield of the 2,6 product here. That's great, but what if we wanted the 2,2 product? There's no way to form the other enolate without allowing equilibration, in which case we run into the problem that we're going to get a mixture of two products, and we have potential double alkylation when we have alpha hydrogen on both sides. So we have a useful way of making the kinetic product, but we don't yet have a useful way of